we're going to continue. So therefore, if we're going to solve for the mid-span deflection having this loading, so you simply have to use this equation. So we have here our you simply have to substitute. So using this equation, simply have to substitute the values. So we have here 600 all over 384 times 5 multiplied to our L, which has 6 raised to the 4th minus 12 times 6 times our B, which has 2 squared plus 8 2 squared. Simplifying this one, we get a value of 7,625 Newton cubic meter cube. Of course, this is a downward. So therefore, however, we have extended our uniform loading towards the support. So we have added a load. So therefore, whatever we've been added should be subtracted. So we have here, we have to have this load to balance to our added load on the top of the beam. So we have here our deflection elastic curve. So therefore, this is the deflection. The deltas is deltas of 2. And of course, the intensity is still 600 Newton per meter. So our B, of course, is this one. And this is our A. So therefore, the formula that you will be using is, you have this formula, EI deltas of 2, which is equal to W's of O, A squared all over 96 times 3L squared minus 2A squared. So if we try to substitute, you have 600 times 1 squared all over 96, then times 3 times 6 squared minus 2 times 1 squared. If we try to simplify, we get a value of 662.5 Newton cubic meter. So therefore, the mid-span displacement is equivalent to EI delta is equal to EI deltas of 1 minus EI deltas of 2. So if we try to substitute the values, you have 7,625 minus 662.5. So we have the value of 6,960 Newton cubic meter. So that is the value for our mid-span displacement for this uniform loading that is acting on the beam. So the next problem is the overhanging beam ABC, as shown in the figure, carries a concentrated load P at the end of point C. Determine the displacement of the beam at point C. So we're given that our figure, we have our action forces, and we're given with the elastic curve. And basically, we have our line, distance A and distance B, as indicated in our beam. So if we're going to draw the tangent line so that we could identify our slope and point B. So we have here this is our elastic curve. So if we draw a tangent line, so we have our tangent line. So basically, this is our sigma sub C, and this one is our sigma sub prime C. So this is actually our thetas of B. So therefore, our displacement at point C, denoted by sigma delta C, is equal to theta B times B plus sigma C prime. So therefore, we have to take note that theta B is the slope angle of the elastic curve at point B, and our sigma sub C prime is the displacement at point C due to the deformation of segment BC. So we can obtain our theta B from the deformation of segment AB. So if we try to use table 6.3 on our displacement and slope angle, so a slope angle from table 6.3 due to this concentrated load would be equal to theta B is equal to P times B times A all over 3 AI. And our sigmas of C prime is equal, this is from table 6.2, is equal to P B cube all over 3 AI. So therefore, if we try to substitute to this equation, we have now delta sub C is equal to PB times A all over 3 EI times B, then plus B PB cube all over 3 EI. And if we try to simplify this one, simplifying further, you have PB squared all over 3 EI times A plus B. So therefore, simplifying further, our sigmas of C, which is the displacement at point C due to the deformation at segment BC, is equal to PB squared L all over 3 EI. So this is downward. So we have our final answer. So you have to take note that as we simplify, we have PB squared all over 3I. A plus B is equal to the length of the beam. So that is equivalent to L. So our final answer is PB squared L all over 3I EI. This is downward. So that is the final answer for this particular problem.